Hello and welcome to 1.5 Atomic Structure and Electron Configuration for AP Chemistry. Alright, so a couple of things before we get started. Make sure that you have a periodic table in front of you, either the AP one or the one that I have loaded, or if you have your chemistry helper from a previous chemistry course, you can use that. Now, in the actual notes, there is a periodic table here that we can use, and then there is a periodic table here that shows the electron configuration orbitals of S, D, P, and F. So any one of those would also work. Okay. All right, so let's go ahead and get started on the notes. Now, I'm going to zoom this in just a little bit. First things first, we are not going to assess, AP is not going to assess quantum numbers to electrons in the subshells. That won't be assessed. So that's kind of part of this data table down here. Also, on 1.5, we're not going to necessarily deal with Coulomb's law and actually do calculations, but you need to know that F is force, Q is the charge of the element, and then R is the radius. So we will be working with Coulomb's law later. The reason why it's on this is because we're dealing with valence electrons and bonding, and the force that it takes to pull two electrons apart or to transfer or to bond and break bonds deals with Coulomb's law. So it's kind of an introduction to Coulomb's law, and there is some notes in there for it, but we're not actually going to do the math for Coulomb's law. Okay. All right, so getting into the notes, you should remember, this was, very basic chemistry. Atoms are made up of protons, neutrons, and electrons. We have in the outer shell, the very last shell, we call those valence electrons. Those are the bonding electrons. You should also remember that if you take protons plus the neutrons, you get a mass number. That's what gives a specific elemental isotope its mass number. Protons should equal the electrons in a chemically neutral element. And ions that are formed can be positive or negative, which means electrons are gained or lost. Okay. All right, now when we talk about electron configuration, it's a way of describing the arrangement of electrons within an atom. And this kind of gets into physics, quantum mechanics, thermodynamic physics. Schrödinger is the one that is one of the, when we went over the atomic structure and periodic table trends, he was one of the people that studied how electrons move in our modern atomic model theory. And he brought in that electrons don't spin like Bohr's model, just in circles around the nucleus, that electrons are waves, and they actually move like waves. So that got into quantum mechanics and how these waves and these electrons have spins, and that got us more understanding about how elements bond with one another. Now, with that being said, we're not going to go in depth with the atomic model other than knowing that N is what we call our principal quantum number, and we can have values of 1, 2, 3, 4, and upwards. Angular and magnetic quantum numbers we're not going to deal with, but when we talk about spin on an electron, spin quantum is ms, and it can be positive or negative depending on how many electrons are gained or lost. And that deals with a Barfoot's principle, where only 2 electrons can fit in each orbital, meaning it describes an up and a down spin. Okay? All right, so let's talk about orbital shapes. There are 4 different cloud shapes. We've got S, P, D, and F. Okay? It talks about that the shape of the cloud of a sphere is the S, and the P looks like 2 balloons tied together. So let's flip it over and actually look at these pictures. So the S orbital is like a sphere. And if you think of math, you got your y-axis that normally goes up and down. We normally have, y and then x, but we're also dealing with z here. Okay, so this is your z, and this is going to be the x. Okay, so it's like taking a graph and putting it on its side, and then you've got the z to show a 3-dimensional shape. Okay, so S orbital is a sphere. P orbital, yes, it looks like 2 balloons tied, or like a figure 8. We also call it the dumbbell shape. And with the dumbbell shape, it can be on the x-axis, it could be on the y, or it can be on the z. So if you have something that's bonded, an element that has a sphere and 3 pi orbitals, it kind of looks like this when you put it together. Within those orbitals, only so many electrons can fit. So an S can fit 2 electrons. P has 3 shapes, and for each shape it can hold 2 electrons in that particular space. So a p orbital can hold a total of 6 electrons with its 3 shapes. Now, D is not on here, but d orbitals have 5 shapes, and with each of them holding 5 shapes times 2 electrons, which means they can have up a total of 10 electrons that can fill up the d orbital. And then an f orbital has 7 shapes, and 2 each means the f orbitals can hold up to 14 electrons. Okay? And it's kind of shown down here, possible orbitals. So if you have n equals 1, you have an s orbital, which can only hold 2. If you have an n2 quantum principal number, you could have s and p could be up to 6 electrons, so a total of 8 electrons in an n2 plus the 2 for n1, which would be 10, and so on. So you got 8, 2, 18, 32. Okay. Right. Now, energy levels are how many spaces or periods of the periodic table relate to the energy levels. So it's the different distances from the nucleus. So this is the nucleus here. You got 1 energy level around it, then it's 1s. 1s, this one is also related to the period on the periodic table. 2s would be period 2, 3s would be period 3. So on the periodic table, we have 7 periods, which means there are 7 energy levels at this time that we can find the electron configuration of any element up to period 7. So 7 periods equals 7 energy levels. And the farther away from the nucleus the electrons get, the less force it takes for Coulomb's law to pull that valence electron off. So, because the bigger you get, the bigger your radius gets. Okay? All right, so that's the notes on that page. So let's talk about a Barfoot's principle. A Barfoot's principle looks at spin. It kind of, Abafu and Hans and Pauli exclusion really gets into this. So we have period 1, period 2, period 3, period 4, and what's this 3D? Well, 3D is the transition elements right here. So why do we call it 3? It's in period 4 because there is not in period 3 a actual transition metal row. So we take one less off and we have 3, 4, 5, and 6. And then 4F fits right in here. So we get 6X or 6S, and then we get 5D, 5D up to here, and then we go 4F and then back to 5D. So this one's really going to help you figure out electron configuration. So when we're looking at Abafu, we're actually looking at how do we represent electrons if we're using this. So let me put Abafu there. Well, each one of these levels, each one of these lines can hold up to 2 electrons on each. And the general rule is for every line, the electrons spin up first and then spin down. We always put the up first, representing electrons. Okay? So that's what this part, each dark line shows an orbital that can hold up to 2 electrons. Electrons occupy the subcells, S, P, D, and F. The lowest energy are closest to the nucleus, so 1s is closest, so it would be very hard to pull those electrons off, where the higher energy subshells are much easier to pull off. And that ties in to Coulomb's law. Okay? It's the force between the charged particles, and that's proportional to the product of the 2 charges. But then the force is inversely proportional to the squared radius. And here's your formula again. Okay? So, the higher the charge, smaller the distance, greater the force. That's why it takes more energy to remove electrons that are closest. So these are going to be all really hard to remove because they're closest, where these will be really easy to remove. Right? So the rules for electron configuration, we've got to be able to write these. So what are the rules? So we have these 3 rules here, Abafu, Hun, and Pauli. Okay? So Abafu says we need to build up. We can't just start putting arrows up here and just put them any way we want. We have to fill up each individual subshell before we move on to the next. When we get to a P subshell, we got to spin up on all 3 before we can backfill and spin down. If we get to D, we got to fill up D all the way across with the spin up before we backfill and spin down. So that's Abafu. Hun's rule is that each subshell should have only 1 electron before it's doubled up. So I can't skip lines. I can't go up, down, up, down, up, 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 down, and then come back here and go down. I have to do it in sequence, in order. And Pauli's exclusion principle is kind of equated with a fingerprint. No 2 elements can have the same set of quantum numbers. Chromium has a different aerospin and a different electron configuration from cobalt, from iron. You can't have 2 elements have the exact same electron configuration or a Abafu diagram spin with the arrows. Okay. All right. Now, another way of looking at Abafu and electron configuration is this. This is another way to look at Abafu. We've got 7 periods. Now, why is there an N8 here? There's no period 8. Well, we've filled up the periodic table already. Okay, so we have all of this. We're up to 118. So if a scientist somehow discovers element 119, where are we going to put it? Well, we would have to create a period 8. So this is the most updated Abafu diagram, and seeing it 2 ways. Now, with the lines, they only go up to 7s, but it does add the 8s down here. Okay. So how do we write electron configurations? Well, the numbers represent the period. The S, or letters, are the subshells. And then the superscripts are the number of so superscript is the number of electrons in that subshell. All right. So it says the electron configuration for nitrogen would be as follows. So you got to think of electron configuration of how many elements do I have to get through to get to the element I want. So we have nitrogen here. It's period 2. It has 7 electrons. How do I know that? Because the atomic number is 7. And protons have to equal electrons. So we have 7 electrons. We got to get through period 1, hydrogen and helium. We got to get through period 2, the s orbital. And then we got to get through these 2 elements to get to nitrogen on period 2, the p orbital. Now, if I count this up, I got 2, 4, 5, 6, 7. So it's in period 2, p subshell, with 3 electrons to get to nitrogen. Okay. Now, if I wanted to do the Abafu, here's 1s, and then now 2s jumps really, really far up here. But I'm just going to put 2s here, and then 2p is slightly above it. 1, 2, 3. So 2p. So, according to Abafu and Hahn, I have to fill the shell before I can move on, and I have to spin up first, then spin down. Then I get to period 2, I have 2 electrons, spin up, spin down. And then for here, I'm in still period 2, but I only have 3 electrons. Well, I can't go up, down, up. That's not correct. You have to fill each of the subshells with 1 electron before you can backfill and start filling in the full suborbital with electrons. That's Hahn's rule. Okay. So that's how you complete the orbital diagram. So if you look and compare it to oxygen, let me zoom this in just a little bit. Oxygen has 8 electrons, so 1 more than nitrogen. So we go up, down, up, up, and then we start to backfill. So now I can start to backfill. Then fluorine, I would put a down arrow here for fluorine, and then a down arrow here for neon, before I could go on to 3s. So that's Hahn and Abafu principles working together, so you complete the orbital diagram correctly. All right, well, let's flip this over and try to keep this in front of you as I do the I do's and the we do's, so you know what you're looking at when we get to electron configuration. Okay. All right, so let me kind of put this off to the side here. So as you can see, here's the electron configuration. Up, down, up, up, or how about this? Well, according to Hahn, we have to fill all the boxes before we can backfill. So this is incorrect because we backfilled before filling this last subshell. All right, now, noble gas and the shortcut electron configuration, how to write it. So when you get down into the lower periods, it gets pretty long with the 1s, 1s2, 2s2, 2p6, and on down to, like, we're down to 6s2, 5d12. It gets to be a lot. So what is the shortcut? Well, if I'm looking at an element, the shortcut is I can go to the previous period, to the noble gas, and put brackets around that noble gas, and then that represents all the elements that came before that noble gas, and then I just have to put the next S or D or P after it. So here is an example of the noble gas shorthand for calcium. So calcium is 1s2, so calcium's way over here. It has 20 electrons, okay? So we got to go through period 1, period 2, period 3, and 4s2 gets us to calcium. So I back up. Argon is the noble gas right before calcium. I put argon, 18, that means I got 18 electrons from argon. Period 4s is my suborbital, and I need 2 spots over to get to calcium, so 4s2. You also can see it written just with argon, because it's understood that argon holds the 18 electrons, and just 4s2. So that's a lot easier to write than writing all this. Okay? Now, it says writing argon as this is the same as writing this. Well, argon, what this means is that argon takes the place of all of this in calcium, and then you just got to tag in the 4s2 at the end. This replaces all of this. Okay? All right, so let's look at some examples and try to figure out the electron configuration. So arsenic. Arsenic is element 33. It's got 33 electrons. So As is 33 electrons. Now ground state means that it's not an ion. It doesn't have a positive or a negative charge. It also means that you're not using the noble gas configuration shortcut to write it. So that's what ground state means. So with that, we've got to get to period. Arsenic is in period 4. So we got to go all the way to period 4 through 4s, the 3d, and then 4p, and we got to go over 3 on the p. So think of it this way, going left to right, you're just kind of reading off the orbitals. So period 1, s is the only suborbital, and there's 2 elements. So I'm going to try to move this one down so I'm not blocking. Okay, so I can use this one. So we got hydrogen is above, I'll put hydrogen here. And then we got helium, so 1s2, 2 elements. Then period 2, so we got 2 elements there, 2s2. Then I come over here, period 2. This is the p orbital. Everything from boron to neon down to radon over to thallium. So this is p, 1, 2, 3, 4, 5, 6. So we got 6. And then here we go with sodium. Sodium is in period 3. There's the s orbital. S orbital is just the group 1 and 2. And there's 2 elements in the s. Then I come over here to 3s, or 3p. 1, 2, 3, 4, 5, 6. So 3p with 6 elements. Now I'm to period 4, so I'm almost there. I've got the S group and S2, so 4s2. And then we've got the D group. This is the first time hitting D. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, remember, D does not follow. It's 3D, not 4D. So it's the first D group. There's 10 elements. Then you got to remember, okay, I'm at the P group, but this is 4 now. So period 4 with P, 1, 2, 3. Now, if you want to make sure that you got it correct, then what you do is you add up the superscripts and make sure it adds up to 33. So we got 2, 4, 6, or 2, 4, plus 6 is 10, 12, 18, 20, 30, 33. Now, I know it doesn't say do the noble gas configuration, but let's practice it. So arsenic is in period 4, period 3, the noble gas is argon. So the noble gas shortcut. So argon gives us our 18, Then we got 4s2, 3d, 10, and then 4p3. So notice, by putting argon there and doing the noble gas shortcut, we're essentially replacing all of this with writing that. Okay, but if it says ground state, put ground state. All right, let's look at the we do. It says write the electron configuration for calcium ion. Now this is an ion. Let me zoom this in just a little bit. So it's +2. Calcium is element 20, which means it has 20 electrons. But if it's positive, that means it lost 2 electrons, which makes it 18 electrons. So we got to write the electron configuration for 18. So it's like taking calcium and backing it up 2 spots. So calcium is here. I lost 1 electron, that puts me to potassium. I lost another electron, so I'm back to argon, so I'm back to period 3. So the complete electron configuration would be 1s2, 2s2, 2p6, 3s2, and then 3p6. Let's add it up. 6, 7, 8, 14, 15, 16, 17, 18. Okay? All right, let's look at the you-do problems. You should have plenty of room to do the you-do problems. You shouldn't have to do it on a separate piece of paper. So number 1 is just like the I do. Write the ground state electron configuration for chlorine. Chlorine is element 17. So you need, and it's in period 3, so you need to show 17 electrons. Write the electron configuration for fluorine, but it's negative. So you might want to put the little negative up there. Okay. Write the complete electron configuration for aluminum ion. Aluminum is 3+. Okay, so that means you lost 3 electrons. And then it says the valence electron configuration for the unknown element is xs2, xp4, where x is the integer. Okay, that's the number. Right. Based on your knowledge of the ion formation, predict the charge for the ion that would form when this element loses or gains electrons. So, if you've got S2P4, what would be the ion configuration? So be careful with this one. It might be confusing to you, but work through it, because you want to look at, can it gain? If it gains, it would have a negative charge. If it loses, would it be positive? Okay? So think out, if it, based on ion formation, what would be the charge for the ion that it would form if this element loses or gains electrons. Okay. Number 5, I want you to write the noble gas configuration for scantium. So scantium is right here. It's element 21. And then in number 6, in the diagram to the right, there are 3 of the orbital diagrams are correct and 1 is incorrect. So I want you to identify first which ones are correct and tell me what element they are, and then tell me which one is incorrect, and redraw the one that is incorrect and correct it and tell me what element that is. Okay? And then for the last one, number 7, when an electron in an atom gains sufficient energy, it can move to a higher energy level, which is further away from the nucleus. This is called the excited state. Write an electron configuration for an excited state of sodium in which one of the p electrons, 2p electrons, jumps to the 3p orbital. So you can draw that out with a BAFU, or you can write the electron configuration. Okay. Again, reason this out what would happen if one electron got excited and it jumped from one of the 2p orbital and jumped to 3p. What would you do to the 2p? And you would put the 3p on there. Okay? All right, so that is your notes and the practice on 1.5 electron configuration and going over the orbital shapes and atomic structure. So make sure you go through and do that practice, and I will see you in class.